Good afternoon, my dear children. In afternoon session, we have see the first topic of Wein's displacement law. In the universe, every object emits radiations. The wavelength of these radiations depends on the objects of absolute temperature. These radiations have different wavelength of all emitted wavelength will not have same intensity. So, according Wein's law state that the wavelength of maximum intensity of emissions of blackbody radiations is inversely proportional to the absolute temperature of the blackbody. So lambda m inversely proportional to the 1 by T, or we can write as lambda m proportionality constant B. Proportionality constant B tells us Wein's constant and into 1 by T. The value of Wein's constant is 2.898 into 10 power minus 3 mK. It implies that the temperature of the body increases, the maximal intensity of the wavelength shifts towards the lower wavelength. Here, the wavelength increases, the temperature body also decreases, which means inversely proportionality. And here, to provide the graphical representations between the intensity of radiations and wavelength in terms of nanometer. So the peak value indicates that all the incident radiations will be in the form of absorptions according to the black body. Okay, this is Wein's displacement law. So graph tells us the peak value is inversely proportional to its temperature. The curve is called as black body radiations curve. Okay, and then next topic, thermodynamics. In previous section, we have studied about the terms of heat, temperature, and thermal properties of matter. So thermodynamics is the branch of physics which describes the laws of governing the process of conversions of work into heat and conversion of heat into work. So the laws of thermodynamics are formulated over the 3 centuries of experiments work of Boyle, Charles, Bernoulli, Joule, Clausius, Kelvin, Carnot, and Helmholtz. In our day-to-day life, the functioning of everything around us, even our body, is governed by the law of thermodynamics. Therefore, thermodynamics is one of the essential branches of in our physics. So, we have more the topics of first one, 8.4.3 thermodynamic state variables. In mechanics, velocity, momentum, and acceleration are used to explain the state of any moving objects. In thermodynamics, the state of thermodynamic system is represented by a state variables is called as thermodynamics variable. For example, pressure, temperature, volume, and internal energy. The values of these variables completely describe the equilibrium state of a thermodynamic system, like as heat and work are not state variables, rather they are process variables. There are 2 types of thermodynamics variables, like as extensive and intensive variable. So extensive variables depends on the size or mass of the system. For example, volume, total mass, entropy, internal energy, heat capacity, etc. The intensive variables do not depend on the size or mass of the system. For example, temperature, pressure, specific heat capacity, and then equations of state. So the equations which connect the state variables of in specific manner is called as equations of state. So first of all, we are going to see the topic of zeroth law of thermodynamics. In zeroth law of thermodynamics state that if a two system here A and B are the two thermal system, okay, A and B are in thermal equilibrium with the third system C. A and B are thermal equilibrium which to each other. Consider a three system of A, B, C which are initially different temperatures. Assume A and B are not in thermal contact with each other, okay, but each of them is thermal contact with the system of C, the third system C. After a lapse, which means small time, lapse means small time, the system A will be in thermal equilibrium with the contact of C, and B also in the thermal equilibrium with the contact of C. So in these conditions, if the system A and B are kept in the thermal contact, that tells us figure 8.1b. So if there is no flow of heat between the system of A and B here, there is no heat flows between the thermal system of A and B because of the both system A and B are in the conditions of thermal equilibrium with each other. So once the three system are in thermal equilibrium, like as A, B, C, or the three system are in the conditions of thermal equilibrium, there will be no heat flow between the same temperature. So they are mathematically expressed here. TA equal to Tc, temperature of E will be temperature of C, and Tb equal to Tc. Here Ta equal to Tb. Then after, whereas T and Tb, Tc are the temperatures of a system of A and B and C respectively. The temperature is the property to determine whether the system or in the conditions of thermal equilibrium with other system or not. So the zeroth law enables us to determine the temperature. For example, when a thermometer is kept in contact with the human body, it reaches thermal equilibrium with the body. At these conditions, the temperature of the thermometer will be same as the human body. This is the principle of using of a finding of a body temperature. In the next topic, 8.6, internal energy. Internal energy of a thermodynamic system is the sum of the kinetic and potential energy of all the molecules of the system with respect to the center of mass of the system. The energy due to the molecular motions, including translations. Translation means linear motions, and rotational vibrational motions is called as internal kinetic energy. We can represent as EK. The energy due to a molecular interactions is called as internal potential energy, represent as EP. So the internal energy we can represent as the sum of the internal kinetic energy plus internal potential energy. Since the ideal gas of the molecules are assumed to have no interactions with each other, the internal energy consists of only kinetic energy part EK, which depends on the temperature, number of particles, and its independence of volume. However, this is not true for real gas like van der Waals gases. In second point, the internal energy is a state variable. It depends only on the initial and final states of the thermodynamic system. For example, the temperature of water rises from 30 degrees Celsius to 40 degrees Celsius either by heating or by stirring. By the final internal energy depends only the final temperature of 40 degrees Celsius and not the way of it's arrived at. Okay. This is, for example, hot object. Internal energy decreases. And internal energy increases, heat flows, thermal contact. And next topic, Joule's mechanical equivalent of heat. In this, Joule's mechanical equivalent of heat tells us the temperature of the object can be increased by heating or by doing some work on it. In 18th century, James Prescott Joule showed the mechanical energy can be converted into internal energy and vice versa. In his experiment, the two Moses were attached with the rope of a paddle wheel as shown in the figure of 8.19. This is Joule's wheels 8.19. So when the Moses fall the distance h due to the gravity, both the Moses lost potential energy is equal to 2 mgh. When the Moses fall, the paddle wheel turns due to the turning of wheel inside. Water and frictional forces comes in between the water and paddle wheel. This is because a rise in temperature of the water. This implies that gravitational potential energy is converted into internal energy of water. So, the temperature of water increases due to the work done by the Moses. In fact, Joule was able to show the mechanical work has been same effect of giving heat. He found that to rise of 1 gram of an object by 1 degree Celsius, so 4.1x joule of energy required to earlier days of heat will be most measured of calorie. So 1 calorie is 4.186 joule. This is called as Joule's mechanical equivalent of heat. So we can move the next topic. First law of thermodynamics. In first law of thermodynamics tells us the statement of the conservation of energy. In Newton mechanics, the conservation of energy involves kinetic and potential energies of bulk objects. But the first law of thermodynamics includes heat also. So the law states that change in internal energy del U of the system is equal to the heat supplied to the system Q minus work done by the system on the surroundings. Okay. So mathematically we can write as del U. Del U represents as change in internal energy. Q represents as heat energy supplied to the system. W be the work done. So the internal energy of a thermodynamic system can be changed either by heating or by work done, shown as below. Here the heat flows into the system, the internal energy increases. The heat energy flows out of the system, the internal energy decreases. So work done on the system, the internal energy increases. Work done by the system, the internal energy decreases. Based on the table, the sign conventions is introduced to the first law of thermodynamics. So increases value becomes, we are put the value of positive, and decreases we put the value of negative. Thus here the system of gains heat Q is positive. The system of losses heat Q is negative. Work done on the system W is on the system, we can W is negative. Work done by the system is W is positive. So provide the table answers of the diagram 8.20 here. So energy greater than 0, work done will be greater than 0. So even though we often explain the first law of thermodynamics using cases, the law is universal and applies the liquid and solid also. And the next topic, quasi-static process. Quasi-static process. So consider a system of an ideal gas kept in the cylinder of volume V at pressure P and the temperature T. When the piston is attached to the cylinder, moves in outward to the volume of the gas will be changed. As a result, the temperature and pressure will also change because all three variables pressure, temperature and volume are the related by the equations of the state PV equal to NKT. If a block of some mass kept in the on the pistons, it will suddenly push the piston downward. The pressure near the piston will be larger than the other parts of the system. It implies that the gas is non-equilibrium state. We cannot determine the pressure, temperature or internal energy of the system until it reaches another equilibrium state. But if the piston is pushed very slowly such that at every stage it is still in equilibrium with the surroundings, we can use the equations of state to calculate the internal energy, pressure or temperature. This kind of process is called as quasi-static process. Okay, so a quasi-static process is in a finitely slow process in which system changes its variables of PVT slowly such that it remains its thermal and mechanical and chemical equilibrium with its surroundings. By this infinite slow variations of the system is always close to equilibrium state. Next topic, work done in volume of changes. Here, so consider a gas contained in the cylinder fitted with movable pistons. This is a movable pistons. Okay, this is a movable pistons. Suppose the gas is expanded quasi-statically by pushing the piston by small distances dx. Since the expansions occurs quasi-statically, pressure, temperature and internal energy will be unique values at every instant. So the small amount of work done by the gas of piston dW equal to Ftx. The force exerted by the gas on the piston F equal to Pa. The formula comes from pressure P equal to force per area. So we can measure the force, piston force F equal to Pe. Okay. Here A is the area of the piston and P be the pressure exerted by the piston to the gas. So work done we can write as dW, Fa we can write as Pa into dx, and AdX equal to change in volume during this expansion process. So the small amount of work done by the gas during this expansion is given as Tw equal to P into dV. Note here it is positive since the volume will be increases. So here it is positive. In general, the work done by the gas by increasing the volume Vi to Vf is given by work done initial and final PdV. So put the value. Suppose the work done on the system, then Vi greater than Vf, then W is negative. Note the pressure P inside the integral equations of 8.17. It implies that the system is doing some work. The pressure need not to be constant. Okay. So this is the evaluated. So integrations we need to first express the pressure function as a volume to temperature using of equations of state. Okay. This is our afternoon session syllabus, which means studied portions. Okay, if you have any doubt, contact me. Thank you.